Car crash deaths all around the world are a huge issue. In Virginia alone, there have been over 800 car crash deaths yearly. Virginia averages a crash every 4 minutes. Those 800 fatalities come out to almost 3 deaths and 163 injuries daily. This has given us the title as one of the most dangerous states to drive in. Well, it's time we change that. What can we do to help raise awareness about these incidents and assist those responding to these hundreds of crashes? To accomplish this, we turned to the internet to find more information. We stumbled upon Virginia's Department of Transportation, who has a public dataset recording crash incidents over the past 8 years. This dataset contains almost 2 million rows, each representing a driver involved in a crash, with 30 columns and varying features about the driver's actions and injuries, but it was too much information. We needed some way to reduce the amount of categories in each column, so we would make groups that would classify these features, taking some down from 56 to about 5 categories. An example is this injury feature, where we reduce any type of injury to just the injury class, reducing this down to a 3-class classification problem. Our thinking was that an ambulance should respond to any type of injury because they may be more serious than they appear, and of course any fatalities need an immediate response. This also makes it easier for us to evaluate important features and reduce the number of resources needed to analyze this dataset for quicker predictions. Now we can take a closer look at our injury classes. In the dataset, there was a large imbalance because most drivers were not injured and the vast majority were thankfully not killed in a crash. We are going to predict these classes. We needed to develop a model. Because this is a classification problem, and almost all of our data is categorical, our first thought was to build a decision tree. A decision tree would also display what features played the largest role in a driver's injuries, giving us more information for what features should be emphasized or we should take a closer look at. So with high hopes, we fed our data into the decision tree and evaluated the results using precision, recall, and F1. Taking a look at our data, starting strong, the no injury class performed exceptionally well, which was expected because a large majority of the data belongs to this class. The injury class performed slightly worse, and the fatality class performed the worst overall, which was not what we wanted to see. If we're going to help first responders to find what crashes need immediate attention, we need to be better. Next, we turned our attention to a random forest model, which would use several decision trees, each given a subset of features, and those trees would individually classify the example and vote for a consensus. Immediately, we see that the model performs similarly to a single decision tree, but the no injury class has a much higher precision, which means the model is more accurate when it predicts that the driver is injured. However, this model seems to never predict the fatality class, which is a huge downfall. Overall, the model performs worse than a single decision tree, so it would need to keep trying. After these two models performed poorly in the fatality class, we wanted to try a boosting algorithm. This would slowly make the minority class more important, so the model would become less biased. Combining AdaBoost with a random forest seemed like the best option, so we fed in our data and waited. This unfortunately still performs worse than a single decision tree. If our model is going to be useful, we'll need to identify fatalities much better. With decision trees proving fruitless, we turned to deep learning methods. Our hope was that this model would be able to identify features that were not obvious to us and use those to make a better prediction. Our model consisted of 3 hidden layers with 16, 32, and 16 neurons respectively, each using the ReLU activation function, before a final softmax layer which would give us the probabilities of a driver belonging to each class. Of course, the no injury class performs well, but we were also seeing better performance for injuries and fatalities. This was officially our best performing model, but the recall of this model was too low for us to stop here. So we again went back to our thinking chairs until finally we knew what we would do. We employed a technique called downsampling, in which we would reduce the number of training samples in both the injury and no injury classes to have a much closer proportion in the dataset. This would reduce the chance of the model becoming biased towards the majority class while recognizing that these classes were still not going to have the same frequency in the real world. With our new reduced dataset, we fed it into our neural network, and we see that the precision is lower than other models, but the recall was much higher. This means that our model is much less likely to wrongfully classify a fatal crash as a more minor one. However, the trade-off here is that this model is more likely to predict that a more minor crash is fatal. With this trade-off in mind, we thought that it is better to predict a fatal crash and be wrong than not predict one at all. In summary, after looking over all of the models that we've developed, we strongly believe that with a little more fine-tuning, the downsampling neural network has the potential to highlight life-threatening crashes versus fender benders, giving first responders more information before arriving on the scene. Remember to drive safe, buckle up, and keep your airbag on. There are too many instances of airbags being turned off, Virginia. Let's be better and keep our roads and our drivers safe.